Let's look at notes for 6.3. We're going to first look at partial fractions and then move on to logistic differential equations. So partial fraction decomposition, this is a method that allows us to take a fraction and to split it up into smaller parts that will be easier to evaluate and to find the integral for. So this method is the cover-up method for non-repeating linear factors. So non-repeating means something like this: x plus 2 and x minus 1 rather than x plus 2 squared times x minus 1. So these are both linear, made up of separate linear factors in each parentheses. So the first step is we factor the denominator. So we're going to, as I go through these steps, we will look at this example. So we factor the denominator. So x squared plus x minus 2, we can factor that to be x plus 2 times x minus 1. So we took care of that. Solve for x for each factor. And what we're going to do is we're going to split this up. One fraction will have a denominator of x plus 2, and the second fraction will have a denominator of x minus 1, and we solve for each x. So that means we're going to set both equal to 0 separately, and x plus 2 equals 0 means x equals negative 2, and if we solve x minus 1 equals 0, we get x equals negative 1. Okay. Next, we're going to cover up a factor in the denominator of a problem. So let's first start off by covering up the x plus 2. Okay. So now we're going to plug in the x value that we're covering up, which is negative 2. So we're going to put negative 2 in for, we're going to cover this up. We're going to cover this up and then replace every x we see with a negative 2. So when we do that, negative 2 plus 3 gives us, negative 2 plus 5 gives us 3. And negative 2 minus 1 gives us now negative 3. So we have 3 over negative 3, which reduces to be negative 1. And so negative 1 will go in the space above the factor that we just covered up. So negative 1 over x plus 2. Okay. Next thing we're going to do is we're going to cover up the x minus 1 in the original, or in the factored form of the original expression. So we're covering the x minus 1, and we're covering the x minus 1 to allow us to evaluate what will be the result if we were to plug in a negative 1. A positive 1. All right, if we plug in positive 1 without covering this up, we're going to get undefined. So we're going to cover up the x minus 1, replace each x with 1. So 1 plus 5 is 6. 1 plus 2 is 3. So 6 over 3 is 2. So now we have 2 over x minus 1. Okay. So we've repeated these steps 2 to 3 for each of the factors, and now this is the same thing as what we started with. It's just that now this is a lot easier to deal with. If we want to find the integral of this, we can just go through the natural log rule. Integral of 1 over u is just natural log of u. 1 over u, natural log of u, with the coefficients negative in front, coefficient 2 in front. And if we have it in this form, don't forget the plus c. This is indefinite integral. We could clean this up a little bit more. Sometimes you may see expressions where if it's multiple choice, for instance, they would maybe want you to a multiple choice answer that's actually showing the condensed form. So what we can do is we can rearrange this, put the 2 natural log x minus 1 in front, and then move the negative to the second term. And we can use the power rule, bring the 2 up as an exponent, and now we can use the quotient property, which is ln of a minus ln of b is just ln of a over b, so in this form. So all these are correct expressions, but sometimes we want to be able to play around with the different forms, especially if it's multiple choice, and let's say this was the correct solution, and we need to be able to work our way down to that. In order for partial fraction decomposition to work, the degree of the denominator must be greater than that of the numerator. When it is not, we look to test out long division method first. So in this case, the degree is higher in the denominator than the numerator, so we know that partial fraction decomposition is a possibility. All right, so moving on to logistic growth. Logistic growth, population that grows exponentially cannot continue to do so indefinitely. After a while, the population begins to compete for resources such as food and water. The growth begins to taper off as it approaches some carrying capacity. So it's kind of some kind of limit, right, of the system. The carrying capacity is a maximum number of individuals of a given species that an area's resource can sustain indefinitely without significantly depleting or degrading those resources. In this case, the growth rate is not only proportional to the current value, but also how far the current value is from the carrying capacity. Okay, so here's an example. Imagine a rumor spreading throughout a school of 2,000 students. The rate at which the rumor spreads is directly proportional to both the students who have heard the rumor and the students who have yet to hear the rumor, as the number of people hearing the rumor approaches 2,000. Okay, the curve for the spread of the rumor might look something like what's shown below. This type of curve is called logistic growth. So follow the red curve, and we see this is what we're going to be expecting when we see a logistic growth curve. So 2,000 students, this is the limit of the growth. Okay? And for quantities y that grow logistically with the carrying capacity y equals L, we can state the relation. So let's first talk about this diagram here. Now, at any point here, let's say whatever is below would represent students who have heard the rumor. Whatever is above is going to be students who have not heard the rumor.